Okay, I'm assuming that everybody has done what I asked you to do, which is master the problem set on fluids and thermodynamics. I think I said. Okay, not much thermodynamics in the basis. Okay, so I'm going to assume it's master. Now, got a cylinder. And I've got a little bit of water in the bottom of the cylinder. You can tell it's water because you see the shark fins. Okay. Now, there's a seal exit from this. Takes me into a tube. And at the top of this tube, I've got a reservoir. Okay. So that if I can get water to come out of the top of this tube, it can go into the reservoir, right? Now, this isn't to scale. The water might be a whole lot deeper, but it might be a really long cylinder. Okay. And there's a piston in the cylinder. And there are parts in the cylinder. One there, one there, one there, and so forth, right? The cylinder is at some temperature so that the kinetic energy of the particle, a big particle, okay? Every particle has the same average kinetic energy when measured over time. Now, there are probably more than 6 particles in there. You know, there might be 6 times 10 to the 25th particles in there. More particles than there are grains of sand in the Sahara Desert. Okay? And you can make that comparison with this sort of information. Since these particles have kinetic energy, they're bouncing among other things. And they bounce off the walls of the cylinder, and they bounce off in the water. The sharks don't get them. Okay. And we might even assume that this water is separated from the gas by some kind of a membrane that prevents evaporation and stuff like that. So the number of particles remains constant. Okay. The picture makes sense. Okay, well, if I give you the number of particles and their average kinetic energy in the volume of this container, can you tell me what the pressure is?
Using the ice.
Yeah, let me pause and talk about this for a second. Okay, so if you know the initial kinetic energy and the volume, picture that's capital V, the volume. and the number of particles. Okay. Well, you know that P equals NKT, where N is the number of particles and K is Boltzmann constant, which is R over Avogadro's number. Okay? And you should know that. I think those are the symbols I use. Yeah, and big N is the number of particles. If it was little n, it'd be little n R2. I talked about that last time. So you need to put all that together. Okay, so let's see, we know the volume, we know the number of particles, we know the temperature. Okay. I didn't say anything about temperature. So what are you going to do about that? Looks like the screen's a little blurry. So, my question is, what do we have here that's related to temperature that allows you to determine the temperature? Well, the kinetic energy, average kinetic energy. And let's put a bar over this because it's an average. Okay. And I'm going to put trans on it. Translation. Okay. Now, why do I put translational on kinetic energy? I mean, it's possible this thing has kinetic energy that isn't translational. Okay, so you've got diatomic molecules. This is a bad model of a diatomic molecule that basically consists of two spherical atoms or cylindrical symmetric about this axis. And they repel each other. So if this end of this molecule gets close to this, they repel each other and go off in their own separate ways. They also will move this way or this way or this way, three independent motions of space, X, Y, Z. And they can rotate about two independent axes, one axis. If it's in this, whatever position it's in, you take any direction perpendicular to the axis and it can rotate about that direction. And then there's another perpendicular direction and it can rotate about that direction. It can't rotate about the axis though. Okay. In the first place, it wouldn't have much moment of inertia. In the second place, those atoms don't really spin. Okay. Yeah, I can qualify that a little bit, but yeah. Just accept the fact it can rotate about two independent directions. And the average kinetic energy of a diatomic gas, the average kinetic energy of a molecule of a diatomic gas consists of three components which are equal on the average. This direction has as much kinetic energy as this direction. Okay, has as much kinetic energy as this direction. 1, 2, 3. They're independent. They're perpendicular. The energy is independent, and independently they can have rotational kinetic energy about two axes. They can also have a vibrational kinetic energy, but for diatomic molecules, it's not that it doesn't exist, it's that it's pretty small. But when you get into big molecules, there can be all kinds of vibration in them, and that also includes energy. Okay. Now, the energy in this direction or this direction or this direction is translational, and that's the energy that you get. Well, that motion is what causes pressure. Rotational motion doesn't cause pressure. Okay. If the molecule collides with part of the surface, it's rotating in this direction, yeah, it'll bounce back, you know, it'll hit it, but it could as well, when it gets around here, be receding. It would lose kinetic energy. You can think of that. But the point is, rotational motion doesn't contribute to pressure, only translation. And that's got to be locked in. It should be, because I'm pretty sure that was in the material I asked you to master. Okay, now, if I'm wrong, well, I just explained it and spent more time explaining it than I should have if you were supposed to know. Okay. Not that I mind explaining it. Now, having explained that, I'll just tell you. Kinetic energy, average translation of kinetic energy is 3/2 kT. That's 1/2 kT for every degree of freedom. The X for the Y and the Z. Okay. So there's a connection that allows you to use the average kinetic energy, translation of kinetic energy, to get the temperature, in which case we can't get the pressure. Okay. If we know that. Now, a couple things about PV equals nRT or PV equals nKT, it doesn't matter. I'm not sure this was in the material. First place, nT or constant, what's the graph of P versus V look like? This is a pre-calculus question. But since nobody ever learns pre-calculus when they take it, you might have a little trouble with it, but maybe not. Suppose X, Y equals C, where C is a constant. Then can you solve for Y? Y equals C over X. What's the graph of Y equals C over X look like? You've had calculus, you've had pre-calculus, one of the fundamental relationships and things you study in pre-calculus. Okay, so you need to tap into your knowledge of functions. Okay, so your equation here, of course, would be P equals, oops, wrong number. NKT over T over V. Either NKT or an RT, different ends, different constants with the same value. So it's this, which is constant over V. Makes sense? Okay, so there's your graph. Now, the reasons are really pretty easy to understand, but I probably don't want to take time to explain right now, but probably pull them out of you at some point. Work done by the gas between volume A and volume B is the integral of pressure with respect to volume. Okay, pressure is just force over unit area. Volume, you have force over length squared times length cubed, like newtons per square meter times cubic meters, right? Which comes out newtons times meters. So the units give you units of energy, and make sure you understand that. I'm not going to belabor it. I'll just say units of energy. You can puzzle that out. Okay. Yeah, this is a big deal because this is a basis for thermodynamics. This is how you get work out of a gas. For example, if we close off the tube up here and heat up the gas, it's going to tend to lift this piston, isn't it? Why? Because the molecules are going to start moving faster. They're going to hit the piston faster, which means there are just as many of them as there were before. They're going to exert more force in the momentum exchange, which you should completely understand. Okay. You know, you got a mass, a particle moving at constant velocity, and a tube moving back and forth like this. Remember that problem? That's your basics for understanding kinetic theory of gases, which is what you need to understand this. Okay. And again, if you're at the point where you can work any of those 19 problems, and they're relatively easy problems, well, lesson is you need to focus on being able to work the problems without having to look at the solution. You can write down all the notes in the world, and that can be real helpful because you do learn by writing things down. But the thing you really learn by writing things down is the solution to a problem you don't have a solution of in front of you. So maybe you take notes on all these problems, then you go back and see how many of them you can work without looking at your notes. And if you can't work well, okay, look at your notes, and the next time you try, you're going to be able to work it. Or you'll be closer to being able to work it. There are only 19 of them. They're not long, okay? Most of them, some of them are a little longer than others, some of them are just real short. Learn to work the problems. That's how you learn the material, so you can pull it out of memory when you try to analyze a situation like this, which isn't in the problems, okay? That makes sense? Okay. So these problems are transition to this kind of analysis. And you can't make the transition if you can't do the problems. Okay. Okay. Well, these are kind of the nuts and bolts that you have to put together. I believe the problems explain why this is. Okay. So I believe you theoretically know how to use this. I'm not sure about that. Okay. Which is why I went ahead and wrote it down. And if the problems tell you why, you should know why. Because the more you know, the better you understand the system. Okay. I keep forgetting what engineering fields you guys are planning to maybe go into. Mechanical, is anybody doing mechanical?
I kind of want to do like a couple.
Huh.
Kind of want to do like a couple different ones. I kind of want to do like a couple.
Well, anyhow, if you're doing anything with mechanical energy, you might end up working with engine. A lot of mechanical stuff in an engine, right? Okay. Okay, well, we can make an engine out of this by using some cams and rods and all that kind of stuff, right? You know how automobile engine works, pistons go up and down. So there are various ways we could do it. By the way, we're gonna do it here because we don't want to get all that trouble. You know, I've got an old engine in the 70s, laying in a barn. Pick it up and have to bring it in. If I was in the Olympics, that's the way. But right now, I had trouble dodging it 30 years ago. Okay. I could, but I wouldn't be able to dodge it now. At least not without risk. So it's too heavy. We can't bring an engine. Okay. But we can. Should have laid my hands and we'll see all those tubes over there and all this and stuff. And there should be one that has a tube coming out the top. See, we can heat that up. We watch how the water from the bottom goes up into the tube. And we put the tube at different heights and collect water at different heights to see how much water we get. Well, that's a mechanical energy. We change the mechanical energy of the system by heating it. Okay, what's mechanical energy? It's a sum of potential and kinetic energy. We got more potential energy when that water's up here than we did when it was down here, right? So that'll be our example of a heat engine, but there are many others. If you understand that one, you can understand the thermodynamic cycle, and that's what I really want to talk about. Okay, so let's say that we're not driving rods and moving drive shafts and stuff like that. What we're doing is we're pumping water up into this reservoir. So we go ahead and put a nail in here so the piston doesn't move. Okay. And what we do is we add some heat. Now this is a thin tube. So you want to understand this. There's very insignificant change in the potential energy of the system as the tube fills. Because it's a thin tube, there isn't much water in there. There isn't much potential energy, but there's a little, and maybe 2 or 3% of the potential energy is in the tube, and it could be accounted for. But let's ignore it. Okay, that's a tube is really thin, and the amount of water in the tube is going to be very small compared to the amount of water in this reservoir. Okay, so we just call the practical work or practical energy gain of the system is just change potential energy, whatever isn't here. It used to be done. Okay. Now, after we heat it up, we get some water in here, right? We've got a lot of water down here. Okay. Maybe there's even a reservoir out here that'll feed this, but it's sealed whenever the engine is running. That could be worked out. That wouldn't be too difficult if you have the right machine shop and the right. Okay. So we heat this up as much as we can. So let's say we're heating it with boiling water. Let's say we start at 30 degrees Celsius and we heat it up to 100 degrees Celsius, right? We can't heat it up anymore because our source is boiling water. Okay. If our source was superheated steam, which would surround this thing and the air would heat would conduct into the cylinder, right? As opposed to like in an automobile engine where you inject a little bit of explosive stuff in there and ignite it. Okay, which is a whole lot quicker. It is not a fast engine. Uh, but there are experiments that haven't really worked out, but theoretically could, where you like submerge this thing in the ocean. Okay. Then you take warm water from the surface and use that to heat the thing. And it pumps water. Or it drives the generator. Okay. Or moves a piston, whatever it does. Okay. So you use the warmer water at the surface, heat it up, and then the colder water below to cool it back down so you can do it again. Well, if we use it in the lab, we heat between 30 and 100 Celsius. We can't really do that. If we get up over about 60 or 70 Celsius, we start deforming the plastic, the bottle that we use. Okay, but you know, if we had a metal container and stuff like that, we could heat it up a lot more than 100 degrees. It used to be use a direct flame. Okay. Anyway, heat this from 30 to 100 degrees. And then we want to pump some more water. Before we pump more water, we got to cool it off. Okay. So we put heat into it to heat it up. And then we got to take heat out of it to cool it back down. It gets up 100 degrees, and before we can pump more water, we got to bring it down to 30 degrees. That wastes a lot of the heat that we put in. That makes sense? You might put in 5,000 joules of heat. And then when we cool it off, you might have to take out 3,000 of those joules, which only leaves 2,000 joules. Right? To change the mechanical energy. Does that make sense? Now, how is it that we take out less heat than we put in? Heating the gas up to a certain temperature, then we'll cool it back to our original temperature, right? Well, we're doing it at different pressures. Okay, like before we cool it off, maybe we take this nail out and let it expand real fast, which uses up a lot of the energy in the gas, which means that the average kinetic energy of the particles decreases. As they hit a receding piston, the kinetic energy is going to decrease. Talked about that last time. You remember? Okay, we talked about a lot of stuff, nobody ever remembers it. So these gas particles hit the quickly receding piston, lose energy, and now we cool it off. Okay, so we got to take less energy out than we put in. And it's that difference that drives the cycle that allows us to keep running the cycle and pumping more and more water into our reservoir. Okay? Increasing mechanical energy with every cycle. Makes sense? Well, what's that look like when you graph it? Okay. Let's look at a P versus V diagram of the cycle I just. Okay, here stands for Kelvin. We could put a degree on here, but I'll just left off. Okay, I'll put it on right now so you don't confuse it with voltage. 1.38 times 10 to the negative 23. Okay. 2 seconds per mile. Gee, I forgot what the units are. You can work it out easily. You know what the units of K have to be in order to multiply by T and give you kinetic energy. So it has to be units of kinetic energy over units of temperature. It's joules per Kelvin. Okay, so surprised I don't remember that. Anyway. Here's our initial state of the system on a graph of P versus V. I'm not gonna bother drawing the axes, okay? Now, we heat this thing up. A little bit of water goes into here, so we have a little bit of expansion corresponding to the volume of the water that goes up, right? But we say that that's negligible. So essentially, we're heating it up without changing its volume. What does the graph look like if we heat the thing up without changing its volume? Well, what happens to the pressure? We heat it up without changing its volume. You can point up, down, or this, or this, you don't know. Goes up. You heat something up, it constant volume, pressure goes up. If you keep the amount of gas the same, if you're allowing gas to escape, of course, you can heat it up as much as you want without changing the volume in the container, but you are changing the volume of the original gas. Okay. So what I want you to focus on is that pressure going to go up. So you got pressure 1 B naught, and now your temperature is just rounded off to 270 K. 373. Say we only get up to 97 Celsius. Okay. Makes sense? Well, there's the first part of our cycle. And what we're doing is we're raising the pressure so that now when we turn the piston loose to expand, or when the water starts pouring out here, pressure doesn't increase anymore, does it? As the water gets up here, it starts leaking out. You don't have any more pressure in this tube than you did just before it started leaking out. It'll continue to leak out and the pressure isn't going to change much. Now, this is the ideal case where there's no friction loss in the pipe and all that stuff. I'm not going to worry too much about that, but we'll kind of measure that in the lab. Okay. So we go from here to here, and now our pressure remains constant. But what happens to our volume? It increases. Okay. This water is leaking, so that membrane, whatever separates the water from the gas, is going to move downward, right? So volume is going to increase some volume V1, which you can easily love calculate in terms of V naught. Okay. So that halfway reasonable. Well, is any work being done? Is there area beneath this curve? Well, the area beneath the PV curve is the same as the integral of P with respect to V, right? So we have, first of all, work equals 0 from here to here because there's no area beneath the vertical line, right? The integral of from A to A of PdV would be 0. You know, integrating this coordinate isn't changing, so it's trivial integrals. Okay, here. What is the integral of PdV? Okay, it's from V naught to V1. Okay, well, what is that integral? What is P for this part of the assignment. What's the formula for P? It's just P1 because P is constant. Because it's blown out here, constant. You have a constant pressure because of constant. Okay. So the water flows up to keep the pressure constant, if you like. Okay, so P is just P1. I would say P1 times delta V being V1 minus V naught. And make sure you understand that integral. I mean, it's a really trivial integral, but make sure you lock it in. Because they're not always trivial. Now what you have to do is you have to return this to its original temperature. Okay. Now, the other thing about this cycle is you have some heat that goes in. You've got heat that goes in from here to here. You got heat that goes in from here to here. So I can draw these cycles in order to get. Let's call this state A, call this B, call this C. It'd be hard to read. This says QNAB. Put in here. Okay. From your source. Here you have QNBC. Goes into the system. Okay. So you can measure the amount of energy. You can ideally calculate the amount of energy to do that. Okay. It goes in from here to here and from here to here. Now, per degree, it takes more energy from here to here per degree. Why? Because you're also doing the work of expansion. From here to here, all you're doing is heating the gas. From here to here, you're heating the gas and lifting the water or driving the drive shaft or whatever you happen to be doing with that energy. All right. Well, then somehow you got to get it back to the original temperature or the original pressure, at least. So what you can do is you can take that deal out, or one way or another, allow the gas to expand. With the tubes, we can have a second tube here that's sealed. Okay. We keep it sealed while the water goes up here, and then we open a valve, releases the pressure, right? Or we could somehow, otherwise, we had a piston, we could just let the piston fly up. One way or another, the pressure is going to go down and the volume is going to go up, right? And what's that going to look like? Well, it's going to look like this. That would be the same curve as this one is, because the temperature is not going to remain constant, or it might not. Okay. Now, there are two ways we could do this. There are many ways we could do this. The two basic ways. One is do it quickly, so the temperature goes way down. Okay. Another way is do it at constant temperature. We just keep the heat on and gradually raise the piston slowly so that the temperature can keep heating. Okay. That would be called an isothermal expansion when we keep the temperature the same, isothermal. The quick expansion, which is what we probably use, is called adiabatic. And no heat goes in. We go from state C to state D. It's adiabatic. No, actually, it shouldn't be state D. You have an adiabatic curve. Okay. In the adiabatic curve, PV to the gamma stays constant. For gamma, if you got air, it's about 1.4. If you got a monatomic gas like argon or something, it's like 1.67. Okay, simple fraction, 7 or 5/3. For a monatomic gas, this is just the ratio of the heat you got to put in. Wait a minute, I say it right. Yeah, this is a ratio of the heat you got to put in to the change in kinetic energy. You got to put heat in to raise the kinetic energy. You got to put heat in to do the work in an expansion, and that's what this is. Okay, and the expansion does work. There's an area under this curve. Now we're not going to get into the detailed analysis of this. Okay, because we're doing a fairly quick overview of thermodynamics, giving you the basic concepts built on what you have in these problem sets. You still need to really get better at it. Okay. So what happens then is the gas expands. It's not going to spontaneously expand forever. It's going to expand until the pressure is equal to the original pressure. Okay. So the pressure becomes equal to the original pressure. Which means it expands and gets to this point. Okay. Now, since you know PV to the gamma equals constant, you can calculate the volume at this point, and then plug that back in here to figure out the temperature. And it's not going to be the original temperature. It's going to still be warm. You're going to get rid of a lot of energy. Okay. Get rid of a lot of energy. And you're going to lower the temperature very significantly. You know, you probably have the experience if you've done around pressurized cylinders and stuff, that if you let something come out of a pressurized cylinder, even an aerosol spray bottle comes out cold. Well, this. And now you return it. So you've been around the cycle like this. Now you return it here. And you out. Oh, okay. You got to take heat out. So you got to cool this thing off one more or another. Now, if it's boiling water and ice water, you can figure out how much heat you got to take out of the water, put into the water. But point is, the heat that you put in here and here is lost through the adiabatic. Okay. Qn is 0, but you do lower the temperature. Okay. And the heat you take out here is less than the heat you had to put in to get from state A to state C and do the mechanical. Difference? In the ideal case, we no friction and everything is the mechanical work. Okay? Efficiency. I'll spell the whole thing out. Thermodynamic efficiency. I'll abbreviate mechanical. Mechanical work divided by Qn minus Ql. Okay. And I think I can't see the whole board, but there. I think it is. Let's just lower the camera a tad and make sure. I can't ever tell whether Zoom is covering up part of the board or not. I can see this. Okay, we got this. That's less than TH minus TC over TH. Temperature here is TC. Temperature here is pH. So if the temperature goes from 300 to 380, as on this first diagram, which we can complete now, okay? Then this maximum possible efficiency, which is the amount of work done divided by the amount of work you put, the amount of energy you put in, is equal to 370 minus 300. I mean, that's easy. That's 70 divided by 373. A little less than 20%. With this specific engine, you never get 20%. And we could prove that. I could put on an exam and ask you to do the interval and stuff like that, but probably won't be that mean to you. The mechanical work is the total area here. The useful mechanical work is only this part of the area, because that's where you're raising the water or changing the mechanical energy, right? But when you do this expansion, you're expanding against the pressure. And you're doing work that doesn't do you any good. But it's still part of the thermodynamic efficiency. So now I'm just using different colors. They're not so useful. Okay. Might be able to tap some of it. You know, if you use an adiabatic expansion, I'd actually be able to use the shaft tap that work. Okay. But in the case of this engine, maybe not so useful. I'll say maybe not so useful. And read that. Okay. So let's talk about it for a minute. You gotta say some of this off screen. All this stuff is stuff you're supposed to know when you come in. Okay. And you kind of knew parts of it. But I repeat, you know it when you can work all the problems. I'm gonna link up a site that just gives you the problems, gives you override of problems. Okay. I don't know how many, I think there might be 740 different problem statements. Okay. Over the 18 problems, I think. Then it's random. So you have as many problems as you want. Okay. You should be able to do those problems. And I'll probably link up that site. It doesn't have the solutions. You've got the site with the solutions. Use those so you learn how to do the problems. Okay. Then it's pretty easy to understand the details of this, but the overall concept of put energy in to build pressure. It doesn't do any significant work. You're just building up pressure, not changing the volume much for this system. Okay. Then now that you got pressure built up, you go ahead and do some work. So you build pressure, you do some work. In this system, build the pressure by raising water in a thin tube. And then you do some work letting it collect in a reservoir up high. So your mechanical energy is changing. Then you got to get back to where you started so you can do it again. Well, two basic ways you do that expansion. Could be isothermal, could be adiabatic. But generally, it's going to be adiabatic. Let it happen quickly so that there's no time for thermal energy, heat, to enter or leave the system. Okay. And you know what I said, you've got Q out. I kind of don't like that terminology as I think about it because it looks like you're taking energy out of the system. I'm going to still include the heat loss due to the adiabatic expansion. Okay. There's Q out. Because that's actually part of the area under the diagram, right? Sorry. Okay, so you cool it off, letting it come back to the original pressure. This is the one on the line. Okay. And then you still got to cool it off. You got to take heat out directly into your cold reservoir. Okay. You say you got the ocean in a place where the ocean's in freezing temperature. Okay. So you got plenty of water to cool this thing off. Okay. That's, you call that a cold sink. You exhaust as much heat as you want to that cold sink. Ideally, not ideally, that cold sink might be a lake that's going to get eutrophied when it's powered by a power plant. So you got to pay a little bit of attention to that. But, okay, I think about that. But might be harmful, might not. Depends on the situation. Okay. That's it. And the idea is that again, heat you take out is less than the heat you put in. That's your, you know, I call that mechanical work. And I really think I'm going to change my terminology. That's your thermodynamic work. Again, your thermodynamic work is total area under this. You just integrate P versus V here, integrate here, and then integrate here. This interval is going to be negative, these intervals are going to be positive. Okay. And this is clearly going to be less than that one. So the area you have enclosed is just the interval from here to here, minus, well, minus the interval from here to here, which would be. Okay. Okay, now I want to talk about fluids just a little bit. Now in lab, it's going to be a 2 liter bottle. But here. Kind of assume it's a cylinder full of water. And here, y equals 0. Okay. And here, y is a function of time. So let's assume this tube is open. So that water is flowing out. What does Bernoulli's equation say? If we compare the state of the fluid at this point, at this point, at this point, C. So A is here where the fluid is, B is down here at the level of the tube, and C is in the outflowing water. Right outside the tube. Okay. So what are the three variables in Bernoulli's equation? Could you tell me? Go ahead and tell me if you can, but let me mute us here. Okay, so what are our variables here? What are the variables in Bernoulli's equation? Well, the symbols are rho, v, y, and pressure. Okay. Now, if this is water, rho is constant. Everything we do in this course, rho is constant. You get into the engineering field, you got to deal with a non-constant rho. You'll have a lot of fun with it. Okay. I mean, you know, like if you're doing aerospace, then you got to take it into rho into account. And it gets really pretty hard. You got to choose a lot. Okay. Just think, things you fly from here to up there in are built by cheating. But built with a lot of testing and a lot of empirical data, so they work. Okay, they're safe. So what changes between point A and point B? Which of these? V, Y, or P? And let V be 1, let Y be 2, let P be 3. Tell me which ones change between here and here. Okay, you're saying Y changes. Okay, anything else? Y can't change without something else changing. Bernoulli's equation says that 1/2 rho V squared plus rho VY, rho GY plus P is constant. It ain't changing, right? So if one of those three things changes, then rho stays constant as it does. Okay, so pressure changes. So Bernoulli's equation can tell you what the change is between pressure here and the pressure here, if you know what the change in Y is, and you know what the density of water is. And it's pretty tricky. I mean, it's pretty easy. I won't say tricky, it's not tricky. Okay. What changes between B and C? Which ones? One changes because the movement has to here, and what else has to change? What else changes? Now, Y changes after a while, the model stops right there. Yeah, pressure changes. What do you say pressure changes? Well, pressure out here is the pressure of the atmosphere, and this is out here. Pressure in here is the pressure they got from the change in Y. As long as V doesn't change, V of the fluid is something we're going to ignore because we assume the volume of this is a lot escaping here in any time interval, short time intervals, much less tricky. So that the fluid in here is actually moving a little bit, it's descending. That's a negligible term as long as your container is big enough and you can flow holes far enough. If you take the bottom out of this container, then that V of the water container becomes significant. Matter of fact, it's going to accelerate downward with the acceleration of gravity and the change in potential energy of either rho g y. Okay, that makes sense. So that's Bernoulli's equation. Now, that's how you do it. You have to look at isolated points. If you have two pictures of this, you have problems. How do you calculate the change in pressure from here to here? Okay, I'll leave that as a question, but you should be able to answer that immediately, having digested the information in the problem section. Okay, so we're going to have lab Friday, 11 o'clock to 2. And we're going to mess with some of this stuff just to make it real. Okay. In the meantime, you need to start on waves, and there's something I wanted to do with waves. Let me tell you just real quickly. When I talk about waves early on, I'm talking about something we call the sine wave. It's moving like this. Okay. It's got slow speed. The distance between peaks is what we call wavelength, and we can indicate that by lambda. Okay. So this is moving to the right. V and lambda are related to the frequency. Frequency is how many of these per second, right? Some point in space, right there's your point of space. See? So if you know the speed and how many peaks per second, you can figure out how far it is between peaks. Trivial. Or very nearly so. Okay. Take that for what it's worth, and you should be able to do the first 8 problems in waves. Starting with number 9, it gets a little more mathematical. We'll talk about it some in lab. Okay, if you get those first 8 digested at least relatively well, they're really easy, most of them. You should try to do so. Pull as much together as you can.